Welcome to Lesson 11a, Stokes equations for creeping flow. In this lesson, we define creeping flow, which is also called Stokes flow or just low Reynolds number flow. We non-dimensionalize the equations of motion and then simplify them for very small Reynolds numbers, which is the definition of creeping flow. First, let's define some length scale, call it L, and some velocity scale, which we'll call U, in a fluid with viscosity mu and density rho. From these we can create a Reynolds number, rho UL over mu, in the usual fashion. For creeping flow, Reynolds number is very small, typically less than about 0.1, although most flows with Reynolds number less than 1 have most of the characteristics of creeping flow. From this Reynolds number, how do we get Reynolds number very small? Well, either rho, U, or L are very small, since those three variables are in the numerator, or mu is big, since it's in the denominator, or any combination of these. I show two examples here. Lava flow has a huge L and a fairly large rho, but U is small and mu is gigantic, so lava flow is an example of creeping flow. On the other extreme, bacteria or other microorganism has an extremely small L on the order of microns. U is also small. The density and viscosity of the fluid can be that of water or close to water, but the Reynolds number is still small. To see which terms in the equations drop out, let's non-dimensionalize the equations of motion. We have continuity, del ui del xi equals 0, call that equation 1, and the momentum equation, which is the Navier-Stokes equation, rho times the quantity del ui del t, plus uk del ui del xk equal minus del p del xi plus mu del squared ui del xk del xk. This is equation 2. We'll make the following approximations and assumptions. Incompressible, ignore gravity, which we already did in this equation, and assume that we have a viscosity-dominated flow. To non-dimensionalize the equations, we need to pick appropriate characteristic scales. We already have U as our characteristic velocity scale and L as our characteristic length scale. We also have fluid properties, rho and mu. What about a characteristic time scale? There's no imposed oscillation period, which could be a time scale or any kind of ramping time scale, so we have to create one out of the existing parameters. We'll use L over U as our characteristic time scale. We'll also need a characteristic pressure scale. Two choices come to mind. You may recall that in the past we've often used rho u squared, but there's also a pressure scale that can be generated as mu u over L.
But how do you know which one to pick?
Well, Harry, I'm glad you asked. I was just about to discuss this. The first one is appropriate for high Reynolds number flows, where inertial effects dominate the flow, and viscous effects are not as important except near the wall. For example, for flows we generally define a pressure coefficient as Cp equal delta P over 1/2 rho u squared. And in our beloved Bernoulli equation, we see a 1/2 rho u squared term with dimensions of pressure. But this one is appropriate for viscously dominated flows. In other words, inertial effects are small compared to viscous effects. Well, that's what we're talking about in creeping flow, so we'll choose this one. So mu u over L is our characteristic pressure scale. By the way, you can verify by plugging in dimensions that mu u over L has the same dimensions as pressure, which in primary dimensions is m over lt squared. Now we have all the scales with which we can normalize the equations. Note that I use the term normalize, which is a more restrictive term than non-dimensionalize. Since we're using the proper characteristic scales, we expect that our normalized variables are all of order of magnitude 1. We'll use star or asterisk to indicate the normalized or non-dimensional variable. Xi star is xi over L, ui star is ui over capital U, t star is t u over L, and we'll set P star equal P minus some reference pressure times L over mu u, using our characteristic pressure scale. Let's plug these into our equations of motion. Continuity becomes del ui star times u from here, del xi star times L from here equals 0. The u and the L drop out, and we get del ui star, del xi star equals 0. Thus our non-dimensional or normalized continuity equation looks the same as its original form. Let's do the same with the Navier-Stokes or momentum equation. I'll rewrite the equation here, ignoring the gravity term. Well, again, plugging in our normalized variables, this becomes rho del ui star del t star u squared over L plus uk star del ui star del xk star u squared over L equal minus del p star del xi star mu u over L squared plus mu del squared ui star del xk star u over L squared. We see some common terms, so what I'll do now is multiply each term by L squared over mu u. When we plug that into these terms, we get rho ul over mu times del ui star del t star plus uk star del ui star del xk star equal minus del p star del xi star plus del squared ui star del xk star del xk star, where the mu u over L squared in both of these terms has dropped out by multiplying by L squared over mu u. And the term to the left of the brackets we recognize, of course, as our Reynolds number. I'll call this equation 4. Well, by our definition of creeping flow, Reynolds number is very small, and since these equations are normalized, all these terms without any kind of coefficients are order of magnitude 1, so the left-hand side is very small compared to the right-hand side. The entire left-hand side of equation 4 is negligible compared to the right-hand side. Thus we have Stokes equations for creeping flow, and going back to physical variables instead of non-dimensional variables, we can write continuity and Navier-Stokes as del ui del xi equals 0. I'll call that equation 5. And del p del xi equal mu del squared ui del xk del xk. I'll call that equation 6. These are in tensor notation. As a quick review, in vector notation, continuity becomes del dot u equals 0, and in Navier-Stokes becomes del of p equal mu times the Laplacian of vector u. Finally, let's look at some other interesting outcomes of these equations, which I rewrite here, using j instead of k as the dummy variable for the Navier-Stokes equation, and we have continuity as well. What happens if we take del xi of the Navier-Stokes equation? Well, we get del squared p del xi equal mu del squared ui del xi del xj del xj. But the order of differentiation shouldn't matter, provided that ui is a smooth continuous function. So we rewrite this equal mu del squared del xj of del ui del xi, but del ui del xi is 0 by continuity. Therefore del squared p del xi equals 0. Again, reviewing our tensor notation, this is equivalent to saying that the Laplacian of pressure is 0. This is an interesting outcome. It implies that in creeping flow, solutions of pressure can be superposed. Since the Laplacian is homogeneous and linear, if we have two solutions of pressure, we can add them up, and the resulting pressure would also be a solution of the equations of motion in creeping flow. Obviously, you need to use gauge pressures, not absolute pressures. You can't keep adding atmospheric pressure to all your individual pressure solutions. This is opposite of what we discussed in potential flow, where solutions of velocity can be superposed, but solutions of pressure cannot be superposed. I won't go through the algebra, leaving it up to the students. If we take the curl of both sides of our equation 6, the Navier-Stokes equation simplified for creeping flow, we can show that del squared omega I del xj is 0, or in vector form, the Laplacian of vorticity omega is 0. This is another interesting outcome of the creeping flow equations. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.